Hello everyone, welcome back to the channel. So we are solving lead code 300 longest increasing subsequence, which is also more commonly known as LIS. Now it's a very standard, a very famous problem, and it's going to help us solve many others as well. So this is video number 2 of the foundational concept series, and just like I said in the first video, this also happens to be a root problem. So in the first video we solved lead code 78, which was subsets, and the main learning from that particular video, I will link it up over here, is that we were able to think of how we generate all the possible subsequences of an integer array and return that as an answer, right? So we were generating all the possible subsequences. In this one we are interested in only increasing subsequences, and we are trying to see what is the longest of all the increasing subsequences we have, right? So let's have a look at what the problem statement says. It says you're given an integer array nums. Now what you need to do is you need to return the longest if strictly increasing subsequence. Like if strictly increasing means this is not strictly increasing, this is also not strictly increasing, but this is, right? So you need to keep that in mind, and you also need to keep in mind that they are not talking about sub arrays, they are not talking about contiguous pieces of an array, they are talking about a subsequence. So whenever we hear the word subsequence, what should come into our mind? We take some of the elements from an array and we skip some other elements from an array. So I'm not going to draw the whole tree diagram all over again, because that is something that we have already done in the subsets problem. But then we are going to take a very interesting test case over here, and I'm going to tell basically how it can very easily be solved. So if we take a very small test case, and it's going to help us a lot in thinking about how this problem can be solved. If we think about it, the answer for this test case is going to be 2. Why? Because you're going to ignore the 10 and you're going to take the 2 and 3, right? So 2 and 3 is basically your largest subsequence, right? If you take the 10, then you won't be able to take either 2 or 3. So how I'm going to do that is, first of all, see, I start again with an empty array, take and skip. If I take 10, it's going to look something like this. And if I take, if I choose to ignore the 10, it's going to be an empty array, right? So I'm not going to draw the whole tree diagram. I'm just going to draw you the path which leads me to this particular answer. Okay. Now I choose to skip the 10. Then what do? I take skip. So right now I'm thinking about 2. I should take the 2, right? I'm going to take the 2. And then similarly, I'm going to take and skip. I'm going to take the 3 as well, right? So this is basically my answer. And what you will observe is that I have a take and skip over here. Let's think about it. Can I take the 2 over here? Can I say that this is a valid increasing subsequence? This is not, right? Because the last element that I visited was 10, and right now I'm visiting 2. So obviously this in itself is not an increasing subsequence. So ultimately this is not going to help me in order to achieve my overall answer, which is the longest of the increasing subsequences, right? So this is not a valid increasing subsequence, which means that I do not have to even think about taking this path. What I'm going to do is, in such a scenario, I just have one choice, which is to skip 2. And similarly, what I'm going to do is I'm going to skip the 3 as well, because if I take 10, there is no option for me to take the 2 and 3, right? Similarly, over here I skip the 2. Let me actually complete the tree diagram, right? If I skip the 2, and then I have two choices, whether to take the 3 or whether to not take the 3, right? So this is the entire complete tree diagram. And as you can see, I have, if I had taken the 10, I did not have a choice of taking any other number. But if I skip 10, I'm getting this particular answer, right? And how I'm going to achieve my ultimate answer is somehow like this. I'm going to since this is the base case, I have sort of reached out of bounds. I'm going to return the, you can say, in this scenario, I can return the length of the array, which is 1, right? It's going to receive 1, it's going to pass it over here, and it's going to pass it ultimately over here. So from the left side of this particular call, I receive 1. Similarly, in this particular call, I made two choices, right? I made two recursive calls, 2 3 and this 3. This is going to return a size of 2, this is going to return a size of 1. Which of them is the greater one? Obviously 2, so it's going to come over here, right? Similarly, from here, it's 1 is the greater of them both, So 1 is going to come over here. Now 2 versus 1, obviously 2 wins, and 1 versus 2, ultimately 2 is 2 is going to be returned as my ultimate answer, which we sort of already knew was the right answer just by visually analyzing, visually seeing what the problem was. Right. So this is how the structure is going to be like, and let's see if we take this approach. Let's see how we can code it up in our in environment. Right. So what we are doing is we are not thinking of any optimization right now. We are just sort of whatever we were able to think of using the concepts of lead code 78. We are literally copy pasting that same logic over here, right? So what I'm going to do is, since I'm interested in the length of the longest increasing subsequence, I'm going to make a function which is, as you can see, which returns an integer, right? It returns an integer at each and every point. So I'm going to say it's going to be an integer function which returns an integer. Similarly, I'm going to start by with the 0 index. I'm going to say, okay, this I need to say that, okay, I am going to sort of keep these all of these states, or I'm going to maintain all of these arrays, right? So I need to be able to pass a current vector over here, and I need to pass the nums, right? Perfect. Okay, so over here I have the solve function. I receive the current vector that I have, right? And I also receive the vector of int and %nums. Now I have again two choices, whether to take or skip, right? Or skip. Now when can I take the current element? I can take the current element when it is when it is strictly greater than the previous element which I just saw, which I had just taken, right? So I need to see if either current is empty, it does not have any element, right? It does not have any element at all, or the last element. So I can, how can I see the last element? I can say, okay, current dot size minus 1, the last element, whatever the last element is, my the number which I'm currently standing at, nums of I, it should be greater, my nums of I should be greater, right? So I'm going to say something like this: my nums of I, the number which I'm currently standing at, should be greater than whatever the last number is inside of current, right? Just like over here, we were not able to take the 2. Why? Because it was smaller than the last number that we had taken. We are going to say, okay, in that case, I'm going to say, I'm going to define a variable over here, int take is equals to 0, and I'm going to say, okay, if that's the case, you what you can do is you can make the recursive call, and you can recursively see if you know I plus 1 and current and nums. But before I make the recursive call, plus 1 also, obviously, no, not plus 1, because what I'll ultimately return is the length of the array from the base case. So I don't need to do plus 1 actually. What I need to do is I need to push back the element inside of current dot push back the current element, right? Nums of I. Perfect. Similarly, skip is simple. It int skip and solve of I plus 1. But if you are skipping the current element, you need to make sure that you are popping it from the array. So you pass in the current over here, and you also pass in nums, right? Perfect. Okay, right. So sometimes it's going to be like we skip some element deliberately in order to find the globally optimal answer, right? That happens over here, and we just return wherever the max answer comes from, just like we did over here. This was returning 1, this was returning true, so this was returning 2, so overall we returned 2, right? In the base case, what we are going to say is, if your index is out of bounds, if I equal nums dot size, then what you need to do is you just need to return whatever current dot size is. You need to return whatever current dot size is, and if I submit, if I see if this passes the test cases, it gives me a runtime error. Why does it give me a runtime error? I'm probably making some mistake. I pass in the nums. I say if I equal nums dot size, return current dot size. Where am I making the mistake? So why does it give index out of bounds if current dot empty, or if nums of I is greater than current dot size minus 1? Initially current is going to be empty, obviously, so it's going to push it back. Oh, I actually did not see this. If your current is empty, you cannot pop back, right? So I need to see current shouldn't be empty in order for me to pop back, right? Perfect. Let's see if it passes all the test cases. It gives us a wrong answer. Why does it give us a wrong answer? It shouldn't actually. um we are returning current dot size. Why is that? So it should um so if current dot empty equal false, so if you have something in the current, then only pop. If you do not, or maybe I need to include this? I think I do not need to include it at all. But no, I do need to include it, because since I am pushing back nums of I over here, I need to pop that number and then make this particular recursive call. So why is it giving us the wrong answer? Let's think about it. All right, so what we'll do is we'll experiment this thing. So I'll cut this particular line and I will paste it over here. So what I'm saying is, okay, I take the current number, I make the recursive call. So taking the current number, exploring, and then popping it back, and then exploring. So if I see if it should actually work, um, let's see if this works. It clearly does, but then I think it's not going to pass the overall test cases, because in this particular approach, the time complexity that we are taking is O of 2 to the power n, and as you can see, the maximum nums length can be 2500, right? So we need to sort of we need somehow to make our time complexity better. Now if you think about optimization, you see, we don't need to actually take care of we don't need to actually make our our state does not need to include a vector. It only needs to take care it only needs to take into account the last number that we have within it. So for example, if I let's say take 2, then I only when I'm further in the recursive tree, I only need to keep this information in mind, that okay, the last number that I saw was 2. Then I take 5, so I only need to know that the last number that I took was 5. So rather than maintaining the whole array, why don't we just maintain what the last number was that we saw, right? And that is pretty simple. So what I'll do is, rather than maintaining an array, I will just maintain a last ref. Sorry, not a last ref, I will say last idx. So the last index which I took, right? Initially it's going to be -1, and I'm going to say, okay, if I'm not going to say current dot empty, I'm going to say if last idx equals -1. What that means is it's basically the equivalent of current being empty, right? I'm not going to say current dot size. I am just going to say I will probably need to maintain a count as well over here. So how many elements have I taken, right? How many elements have I taken? I'll just keep a count over here. I think we will need that. So what I'll do is or no, I don't need to return count. I'll just sort of whenever I'm taking something, I will make the recursive call as 1 plus the recursive call, and whenever I'm not taking something, I'll just simply make recur as it is. Okay, perfect. So I don't actually need to pass this. All right, makes sense. Then I just need to make all of the other changes that are there. So I no longer have nums. I need to see, it should be nums of I should be greater than the last index that I took, right? Nums of last index, the basically the last number that I took and moved forward. right? That case, and over here I do not need to pass the last index. Over here the last index is going to become I, because that is the last thing that I have taken. I do not need to do this at all. Perfect, makes sense. I just need to include a +1 over here, because whenever I'm taking something, this +1 means that your basically your array size has sort of incremented by 1, right? And skipping means your array size does not change at all. And if you're out of bounds, you just need to return 0, right? Now, why have I made these changes? Is because these changes are going to make it easy for me to memorize the solution, right? And you know why I did not sort of take the exact value over here and the last index, is because last index can at most be 2500, but if I had taken the exact value, that exact value can be up to 10 to the power 4. So that was a clever bit of memorization as well. So I and last index both can at maximum go up and until 2500, right? So I'll make a dp array of a 2D dp array of that much size, and I'll just initialize it with all negative ones, right? Pretty standard memorization that you have. So size of TP, and I'm going to check, okay, first of all, cache all the results, and then if they are present in the cache, just return them from the cache. So if dp of I previous idx if it's not equals to -1, if it has some other value, just return it from the cache, right? Previous idx. What this does is basically it reduces our time complexity from o to the power 2n to a simple o to the power n, right? And the thing is, previous idx is not there, it's actually last idx. And one more thing that I'll need to take care of is that since initially my last idx is -1, I need to do a +1 over here, and similarly I'll just increase uh, this particular size by 1. Last idx +1, wherever there's last idx, I will just plus it by 1. Last idx +1, right? If I see if it passes all the example test cases, does not. Previous idx, last idx, sorry, last idx +1, actually, not last idx, sorry, my bad. Okay, let's see if it passes the test cases. It does not. Why does it not pass all the test cases? Oh, I accidentally added +1 to over here. I shouldn't have. I only needed to add it wherever there is a caching protocol, right? I accidentally added it over here in the if condition. Right, this passes, and if I submit this code, let's see if it passes all the other test cases as well. It very clearly does. So I hope you found the video helpful, and I will see you in the next one.